So today we will do discriminant analysis some more. Hopefully we will finish. I can't guarantee it. I think doing nearest neighbor classification was pushing it a little bit. So I crossed that out. Project number 2, again, I think it was on Saturday. I put in the discussion board. Let's just move it back to Friday, November 14th at noon. The reason why I did that was I wanted to make sure that we actually got through discriminant analysis fully before the project was due. Are there any questions? Okay. So let's just review a little bit. So discriminant analysis is one of many different techniques, where not one technique is always going to be better. One of many different techniques used to try to predict an observation's group. Or you can think of it another way, what population did a particular observation come from? And we use a set of independent or explanatory variables to help us make this judgment. And a key thing is coming into this, in terms of our sample itself, we know what group each observation came from. Okay? And so because we know that, then the things that we need to calculate are as follows. We're going to estimate the group mean or population mean for group I. And for now, we've just only talked about, let's say if I have 2 groups. So I will be 1 or 2. So we estimate mu sub I. We also estimate sigma, let's say the pooled covariance matrix across the groups. And the way that we do that is in a very similar manner to how you estimated a pooled variance in your first stat course when you looked at a hypothesis test for the difference of 2 means. It's essentially the same equation, but now we have matrices. And so with that then, there are 2 main ways to implement discriminant analysis that we're going to focus on in this class, and they're closely related. And they will always give you the same results. Okay? One is we compute what's called the Mahalanobis distance. And so the word distance there means what we're trying to do is calculate how far is our particular observation of interest. Let's call it X. How far is it from that group mean? And so you would think, okay, if X is closest to the group mean for group 1 versus group 2, well, then X probably came from group 1. That's the whole idea behind it. Now, to calculate this distance, we don't use exactly the same equation as what we saw, for example, with cluster analysis. And what we do is this. We take X, we subtract off a particular estimated mean that we're interested in. Do note that is bolded, even though it might not look like it. And then, so that gives you the distance for the mean, but we also take into account that we can have different covariances and variances for each variable. So we put that estimated covariance matrix in there too and invert it. And then we multiply again by X minus mu hat. Notice how similar this is to actually something that we just talked about. Suppose we had just one variable, X minus mu over sigma. How about we square it? That's essentially what this is if we only have one variable. Okay, that's all we're doing. Now, so we calculate 2 different distances. The distance that's the smallest corresponds to the group that we predict for X. Now, we can go one more step. We could take those distances and basically compute a number, or we take these distances and we rescale them so that we always have a number between 0 and 1, just like a probability. And so here's just our little rescaling equation. We get what's called posterior probabilities. And in this particular case, if I had, let's say for group 1 and group 2, let's say if I had a posterior probability of 0.6 for group 1, 0.4 for group 2, since 0.6 is higher than 0.4, I would predict group 1 for that particular observation. That's how it works. All it is a rescaling of these distances. Okay? So now let's take some time to look at how we could actually do some of these calculations ourselves in R without necessarily using the LDA function that we saw last time. I mean, as you can see here, the calculations aren't going to be too difficult. Calculate two means, calculate two covariance matrices, get that pooled covariance matrix, calculate a distance, calculate a probability. That's it. So let's take a look at how we can do that in R. So to show you where we're at in the notes, as a reminder, we started doing a little bit last time. This is like about 19 in the notes. Okay. So let's take a look at our data set. Okay, so there's our data. Notice the very last column is good. That's what tells us what group we're in. Good equal 1 means it's a successful place kick. Good equals 0 means it was a failed place kick. And indeed, we do have some failures. You can see right there. Okay? Now, what I would like to be able to do is pull out observation 1 from this data set, but I don't want the good variable. I only want all the other, let's say, independent variables. This is going to be my X that we had saw on that Word document. So to pull it out, what I can do is this. I can say, I just want row 1 a place kick. I pulled it out, but also I do not want the good column that happens to be column 9. So I can say -9 and not include the good column. Now, I also like to be able to tell R, hey, I'm going to do some matrix calculations, some multiplications and stuff. And so could you please treat this as a matrix? So I say as.matrix. Okay, looks the same, but now R's think of it as a matrix. And lastly, if I wanted to transpose that so that I had a column vector instead, which is what X would be, there's my column vector. So if we put then all those results into an object called obs1, for the lack of a better name, there we go. Okay, next. What I need to do is split up my data set into two parts. The part that has good equals 0 and the part that has good equal 1. And the easiest way, at least I think, to do this is I do some logical comparisons. Let's see here. So if I say place kick $good equals 0, what that tells R is, hey, let's compare all those values in good. Is it equal to 0 or not? And I'm going to return trues and falses corresponding to that. And since this is a kind of a large data set, I'm not going to print off every single one. How about the first 20? And so you can see, for example, there's a true, there's a true. That corresponds to this one and this one. Okay? And so then, when I combine that with the row index for place kick, what's going to happen is that R is going to say, okay, I have some trues and falses here for the rows. I'm only going to return the rows that have a true. So do that. I put the results into pop0, for the lack of a better name, meaning it's the sample that came from population 0. And if I do a head on that, we can see that indeed we have goods. Oops. Let me do it one more time just to show you. We do have all the goods that are equal to 0. Notice this distance of 42 yards there. Here's the distance of 42 yards there as well. Okay. I want to rerun that code again because I do not want the good variable in there exactly. I'm going to do exactly the same thing too for the good equal ones. And then I need to find, well, what was the sample from the good equals zeros? What's the sample for the good equal ones in terms of the sample size, I should say. And so I can say, what's the number of rows of this data frame pop 0? What's the number of rows for the data frame pop 1? And this is what we get. Notice the big difference there in terms of the number of failures versus the number of successes. Take note of that. That's going to be important for us later on. It's actually going to cause us some problems. So next, I need to find the estimated covariance matrix for the data that's in pop 0. Also for pop 1, I'm going to put that into objects sigma.hat0 and sigma.hat1. Just to prove to you indeed that this worked. There's for the zeros. Next, let's find that pooled covariance matrix, what I call sigma hat. And so I just simply write in the formula in the formula that we have. Let me just emphasize this. Notice how I have a 1 in a subscript, a 2 in a subscript. In my syntax that I'm using here, I'm using a 0 as the 1, a 1 as the 2, just because it just makes sense, because I have a good equal 0, good equal 1. So I translate that formula into R. There's my pooled covariance matrix. Then I need to find my estimated mean vector for the zeros. The way I can do that is use the call means function, which just finds the means of all the columns. And so I do that, and also I say, hey, let's treat this as a matrix. Do that for mu.hat0, mu.hat1. Okay, so there we are. Next, let's do the Mahalanobis distance. So here's my x, obs 1. I subtract off the mu hat for group equals 0. Use matrix multiplication to get the inverse. I say solve that pooled covariance matrix. Matrix multiplication, obs 1 minus mu hat 0 again. I get my distance. I put that into D0 for the distance to the good equals 0 group. Do the same thing for the D1s. This is what I get. Okay. So I have two distances there. What should we predict as the grouping for observation number 1? Success. Yeah, success. The good equal 1 group. Because that distance is smaller. Okay. Next, we can rescale this to be a 0 on a 0 to 1 scale in terms of think of it as a probability. And so I just simply program in that expression that we saw before. Here's prob 0, prob 1. Notice that probability for group equal for the good equal 1 is quite high. Therefore, we say, I'm going to predict good equal 1.
Will these two ways of doing it always produce like the same outcome?
Yes.
Or if they're like really close, is it possible that one could be a little bit different? Or
They will always be the same. Again, all it is a rescaling, a numerical rescaling. Any other questions? So I have put questions on a test before where I say, okay, for observation 10, show me how the calculation's done. Either maybe even have you write it out only and not actually do the calculation in R, or I might just say, just show me the code, actually implement the code in R for that particular observation for that particular data set. Okay? So if you remember last time I said that there's some stuff that we're skipping. it has to do with what's called a linear discriminant rule, which is a different way to think about how these results come about. I chose, again, to skip it because, one, it's harder to, R's functions do not, in terms of the LDA function, do not reproduce it exactly. And also, it's just another way to do the same thing. And so that's why I kind of made a last minute decision where I'm going to remove that from the notes. So that's why you see the blacked out area there. You are not responsible for that kind of stuff. And so also, if you remember, we are going to be very interested in the accuracy. How well do these predictions work? So if I had, let's say, a failed field goal I observed, how likely is it for me to get that prediction that's a failed field goal correct? Same thing with a success. Okay? And there's different ways to measure how well this discriminant analysis works. One is what's called resubstitution. And basically, we did one small aspect of resubstitution just now, where we used the entire data set to try to predict observation 1. So observation 1 was actually used to help predict observation 1. And you might be worried, okay, well, does that maybe introduce a little bit of bias? Well, yeah, it could. And so we'll talk some more about how to measure accuracy as we go along here today. Now, another way to do all this is through what's called cross-validation. So if I wanted to predict what grouping should be for observation 1, what I could do is simply remove observation 1 temporarily from the data set, do all the exact same calculations I just did, and figure out, well, is this predicted to be a success or a failure? That's cross-validation. Then I can put observation number 1 back into the data set. Then I could do a similar thing for observation 2. So in the LDA function, to implement it, we looked at this function a little bit before. Again, I can say formula, similar to what you have for the LM function in R for regression analysis, and also many other regression type of models in R. We say formula, then you put in what is your grouping variable, good. So you can kind of think of this as a response variable, although it's not necessarily that exactly. And then we put in all of our independent variables. I say where my data is, and then when I say CV equal true, that means I want to do cross-validation. This prior, something I said before, don't worry about for now. I still don't worry about it for now. We will get to that. And so I put all the results into an object called DA2 because I'm doing discriminant analysis. This is the second time I've done this. I can see information about what's actually stored in DA2. And the most important thing, or two important things for us, is the posterior component of the returned list. Observation 1. Here are the posterior probabilities. Observation 1 is predicted to be a success, the good equal 1 category, because that probability is so large. This probability, you can compare it to the one that we just did, and you can see they're kind of similar. Why, in the end, do you think that they're so similar? So observation 1 was not being used here to predict what the posterior probability was, or to estimate it. The sample size is so large that whether that particular observation is in the data set or not is going to have a very small role. That's why. And so that's where, resubstitution in the end might not actually work that badly if you have a very large sample size. The class component of the list tells us, is this then predicted to be a 1 or a 0? So now you would like to be able to say, overall, for all observations that we use cross-validation with, how good did this do? And so what I've done is I've written a function for you to help you out called summarize.class. On your own, I want you to take a look at the components of this function. What I'm just going to focus is on what information do we need to pass into it. Simply, it's just 2 bits of information. The first, excuse me. The first argument in this function is called original, meaning what was the observed group for those observations in that data set. And then the second one is classify, meaning what are we predicting it to be based upon the discriminant analysis. So I can run this function with summarize.class original, place kick, $good. So again, what was actually observed. Classify is equal to DA2 $class, which is exactly what we saw right there. That came about through cross-validation. So R is going to do some calculations, and this is what's returned. So on the rows of this 2x2 table, we have a 0 for original, and let's match it up with the column for classify is equal to 0. So what this 124 represents is that 124 times we observed a failed place kick, and it was correctly classified as a failure. 39 times it was incorrectly classified or predicted to be a success. 988 times an observed success was predicted correctly. 274 times it was incorrect. Let's now look at the actual proportions that we got in terms of correct. Notice each of these rows adds up to 1. The reason being is this 0.7607 is 124 over 124 plus 39. So we had a total of 163 failures in the data set. 124 times we predicted it correct. So our accuracy for the failures is 76%. The accuracy for the successes is 78%. The overall correct percentage is 78%. So that is, 124 plus 988 over 124 plus 988 plus 39 plus 274. So when I do this myself using this kind of a method or other methods that we'll talk about later in the course, the 3 things I focus on are the overall correct percentage, the correct percentage for one of the groups, the correct percentage for the other group. We, of course, want these to be as high as possible. Next, I use summarize.class now with when we did resubstitution last time. And notice I get exactly the same thing. That's not going to always happen, but it just happened this time. Normally, I would expect resubstitution to give you at least a little bit less accuracy. I'm sorry. Excuse me. I would normally expect it to be a little bit higher accuracy because it's going to be biased. Now, also with this data set, I had a separate validation data set or a test data set that I could try this all out on. Let's see what happens. So I can take, let's see now. So this DA1, this was what we produced last time. This was from using resubstitution with the LDA function. You can go back and review that on your own. I can then use the predict function with the results from resubstitution. But for new data, I put in this data set that it's called valid. If you look at my program, there's a data set called valid or validation data set. I put the results into pred.valid. You can see the posterior probabilities that were produced. Also, a classification will be produced too. So if I run summarize.class with this, I get similar results. My overall correct percentage is 76%. Again, this is meant to be more of an unbiased estimate of how good this method will work. And because of that, I would expect this to be typically less than what I get from resubstitution, and very often less than what I get from cross-validation too. So this is what we got. Any questions? Now, this table that we see here, actually kind of split across the page, has a name that unfortunately has gained traction in the world. Rather than just calling it like a classification table, which statisticians have always called for a very long time. Once computer scientists also got in our field and doing what we did, they decided to do some of the same things and give cooler names than what we use. And so they call this a confusion matrix. So if you ever see that name, that's where it comes about. I remember the first time I heard that name's like, oh, you got to be kidding me. Why? Why do you need to name it that? It's just classification table. Okay. Let's do some generalizations to what we just did here. One that we're just going to talk about a little bit here because it's hard to implement. Well, it's not necessarily hard to implement. It's just most software packages will not have an easy way to implement it. I think that's the better way to put it. And so for that reason, people take this into account, what I'm going to be talking about next year, usually using some other methods instead. So sometimes a particular kind of error that you can make in terms of your classification, your prediction, can be more important to avoid than another kind of error. And so you would like to maybe take that into account in your analysis. So we'll talk about how you can do that here. Also, sometimes the number of items in one population tend to be larger than in the other population, or the number of items in one group is a lot more than in the other group. We saw that with the place kicking data set. So far, basically what we've assumed is for place kicks, half the place kicks should be successful, half should be failure. If you're a football fan, you know that just doesn't happen. Obviously, there's things that underlying factors, but overall, that's not going to happen. And so we like to be able to take that into account. And so we'll look at how we can do that. And to help you understand, especially that sometimes certain kinds of errors or classifications that you can make are more important than the other, let's talk about diagnostic testing for an infectious disease. This is actually one of my research areas. And we'll do a simple HIV example here. Let's say for a set of people, you know whether or not they have HIV or not. And we'll say yes or no that they haven't. Maybe you're testing out a new diagnostic method, a new kind of test, RT-PCR kind of test where you want to say, hey, does this work or not? And so you give this test to these people, and then you record the results corresponding to are they truly positive or not. And so, of course, if a person does not have HIV and the negative test result comes about, hey, we made a correct choice. If they do have HIV and it's a positive test, hey, we made a correct choice, but then also we can have an incorrect choice too. Now, for HIV testing and for many infectious diseases, one of these types of errors is more important than the other. The error that's more important to avoid is that one, where somebody has HIV, but the test comes back negative. The reason why that's so important is because if a person thinks that they don't have HIV, they unfortunately could spread it to others. Okay? We want to avoid that. And so because of that then, we might want to take that into account in our analysis. And so to do that, we can use what's called a cost function. So we can refer to something as C of I given J. And all that is a fancy way of saying, what's the cost of classifying an observation as from group I, given it was actually from group J. So if I had, let's say, C of 1 given 2, what's the cost of predicting something to be from group 1, given it was actually group 2? And then you could also look at vice versa. So far, basically what we've done is we've assumed the costs of making those errors are equal. But if you think this particular error is more important to avoid, well, then that value of that cost should be higher. It's a numerical value. That cost should be higher than the other costs. That's how you can take into account. The problem, though, is then it becomes kind of arbitrary. You know, should I set this, let's say, equal to 10 and this equal to 2? Maybe it should be 20 versus 2. And it becomes arbitrary in some respect. And that's an unfortunate aspect of this. Now, in terms of your populations or your groups having different probabilities of, let's say, being group 1 versus group 2, in terms of the stuff that's in your sample, we can set P sub I to be the prior probability that a randomly selected observation comes from population I. So, maybe, for example, with the place-kicking data set, I could say, instead of using 1s and 2s, I'll use 0s and 1s. P sub 0 is, let's say, maybe 0.12. P sub 1 is 0.88. Meaning I'm going to have a lot more successes. I know I will when I play football. So I wanted to take that into account. Now, there's some other stuff here that's blacked out. You are not responsible for that. It's interesting, but in the end, I think in terms of our time's best put elsewhere. If you have taken a mathematical statistics course and heard something called a Bayes rule, this is what this stuff starts talking about. You're welcome to take a look at it, but you're not responsible. The main thing I want to do is get down to here. This is what you're responsible for. Here's how we can take into account the prior probability and the costs. If you want to know more about how this equation comes about, that's the stuff I blacked out. Sorry. Basically, what we can do is change our distance that we're using to be of this form here. Notice that essentially we have the same thing here that we had before, but now we have the natural log of P sub I times the cost function. This simply ends up allowing you to take into account this extra stuff. Now, how can we implement this all in R? Some of it's easy, some of it's not. Now, in the LDA function, we talked about a few minutes ago, we have this statement, prior equal C parentheses 1 comma 1 and parentheses divided by 2. What that's basically saying is this. I'm going to put a prior probability of 0.5 for, let's say, group 1, a prior probability of 0.5 for group 2. That's all that meant. The reason why I did that was because to show you some of the introductory math elements of how to do this was just a lot easier to motivate how Mahalanobis distance comes about. Now, though, notice if I have to take into account those different prior probabilities, well, first of all, let me say, notice if I put 0.5 here for population 1, 0.5 for population 2, it's not going to matter because it's exactly the same number that you're subtracting from that stuff that's on the left. Okay, so that's why I never had it there to begin with. But what we could do instead is what we could say, well, let's put C point, let's see, what did I have here? 0.12, 0.88. I could put that in there for the prior argument of LDA. The reason why I chose those particular numbers was I think that was essentially about the observed proportions that we had from this failure group, the success group. And actually, by default, R assumes you want to use the actual observed proportions from your data set. And because it's the default, you don't even need to specify it. In fact, what you'll see from now on, we will always use we always will use these prior probabilities that are what are called proportional to what you actually observed. You'll see as we go along and actually implement this code. The actual formal argument value is called proportion. But again, that's the default. Now, if we wanted to, we could also use this prior argument to help us get the costs in there as well. And it's not of interest to us why these equations come about, but you could use these prior probabilities of P1 star, P2 star to get the costs in there. To be honest, I never have seen anybody implement discriminant analysis and do this, but it is possible. Again, the reason why I don't see that is because there's other ways to include costs from other methods that are easier. Okay. So another assumption that we've been making so far is that we have equal covariance matrices. Well, you could have unequal too. And notice what happens to our distance measure. It just changes a little bit. Now we see how the different covariance matrix for that particular group or that particular observation comes into play. And notice I say Bayes rule. Yeah, this is the problem with the stuff I blacked out. It's explained a little bit more in the Bayes rule section about why this equation comes about. So, sorry, but I'm just not going to go over it for us here. And you, again, not responsible for how it comes about. And I'm going to do another little waving my hands one more time. So when I implement discriminant analysis using this distance measure, and of course I could do posterior probabilities as well with this distance measure too. It's the same formula, but I just have a DI star star instead of just DI. When I implement discriminant analysis using or allowing for different covariance matrices, the name of that particular procedure is called quadratic discriminant analysis. Here's where I'm going to wave my hands again. I think this might be a record for me of waving hands in a class. I'm sorry. Remember how I said there was something called a linear discriminant rule? Let's actually go there. And we skipped it. So basically, the main thing to get out of this, you can take from the likelihood function rule, do some mathematical simplifications, and you come up with what's called a linear discriminant rule, and just gives you another way to do exactly the same thing that we've been doing in terms of saying this is predicted group 1, this is predicted group 2. This used to be the way that people would focus on teaching discriminant analysis to people. I went away from that about 10 years ago. And I focus more on the Mahalanobis distance rule and also the posterior probability rule. Usually in the past, though, I would always say, yeah, this is just a different way to do this stuff and just move on. This semester I decided just to even just skip it. But in the end, there's basically a linear function in there. And that linear function is what lends the name linear discriminant rule. Now when I have different covariance matrices, I end up having a quadratic function and an expression similar to this, and that's where quadratic discriminant analysis comes about. Okay, so big picture. We now have two different types of discriminant analysis. Quadratic, where you assume your covariance matrices are unequal. Linear discriminant analysis, where you assume your covariance matrices are equal. To do the linear, we use the LDA function. To do the quadratic, we're going to use a function called QDA. Almost always, again, we will use priors proportional to what was actually observed for each group. So we won't even state that prior argument. We'll just go with the default. Now you might be wondering, well, how do I know which of these methods to use? I used to teach this. I don't anymore. You could actually do a formal hypothesis test. Are the covariance matrices equal or not? You know, if you reject, okay, then you should use QDA. If you don't reject, maybe you could get away with LDA. That seems like a logical approach. That would be, well, it is a logical approach. You'll still see people do that. One could say, why not just always use quadratic discriminant analysis to be safe? Because when are two covariance matrices ever exactly equal to one another? Probably never. So just use quadratic. The problem, though, with that is you get into something that can happen in statistics where you could estimate more and more parameters, and at least, let's say, get maybe a little bit of a better fitting model as you keep on estimating more and more parameters. Then the problem, though, is when you go apply that model someplace else, you've overfit the model, and the method just doesn't work well. And so, because of that, then, I would not recommend saying always use quadratic discriminant analysis. Because sorry if this wasn't clear, with quadratic discriminant analysis, now you have more parameters you need to estimate, because now you have those two covariance matrices to worry about rather than one pooled one. So that's the problem. Quadratic allows you to, or forces you to estimate more parameters. So instead of solely relying on the results of a hypothesis test or playing it safe, I go with what one of the recommended books does. One of the recommended books for our course, and that is just do both. Do LDA, do QDA, look at your accuracies, pick the one that does the best. As long as you don't have an extremely huge data set, the computations aren't going to be that bad to do both. Okay. So let's apply some of this stuff. So with the place-kicking data set again, we are now going to talk about, this is important to put in your notes, the correct way to do the analysis. So we had done some other stuff before just to help to show some of the aspects of these methods. Now we're going to do the correct way to do the analysis. Note that if you were to average all the ones and zeros for the good variable, you get the proportion of successes in the data set. The proportion of successes is almost 89%. To do LDA, linear discriminant analysis, I'm going to put the results into DA3. Again, formula equal good variable, tilde, all my independent variables. Data's in place kick. We are not going to do cross-validation yet, so I'm going to put false. Then also create an object called DA4 with the LDA function, where this time we will do cross-validation. Okay? Next, let's look at how accurate these predictions are. So I go to my summarize.class function. Original equal my good variable. Classify equal. I'm going to pull out the cross-validation results from DA4. This is what I get. The overall correct classification rate is now 87%. So that's better than what we had before. I'll talk more about that if that's really good or not coming up. Notice the successes. We get about 94% of them right. But now we have some more problems with the failures. Only 37% right. Next, let's go to the validation data. Note, I'm using DA3 here. This is from using resubstitution. In order to predict for the validation data, this is important, you have to use the results from resubstitute, the results from LDA when using resubstitution. It doesn't make sense to do the cross-validation way because that's cross-validation. With the validation data set, that's a totally new data set that you're just trying to predict with. So I put the results into pred.valid.3 and I look at summarize.class. Overall correct percentage, 85%. For the good equal ones, 93% about. For the good equal zeros, about 39%. Okay. Let's see to make sure I talked about everything. Yes. Let's now do quadratic discriminant analysis. So this is the first time that we've seen the QDA function in practice. So I said QDA. The syntax is essentially the same as what we just did with LDA. I just put QDA instead. So this is for resubstitution. And then, where is that? There it is. Here's for cross-validation. Let's look at the results from cross-validation using summarize.class. Overall percentage, 86%. The correct percentage for the successes is 91%. For the failures, 45%. With the validation data set then, overall correct, 84%. We have similar results for the good equal ones, good equals zeros. And then we get to a table that looks like this. So typically, when one uses discriminant analysis, and also with other methods that have the same goal of trying to predict, you always end with a table that looks like this, where you put all your results that you got so far, put in the accuracy values, and then from this table, you can make a judgment of which method should I go with. So we can see that overall, looks like linear discriminant analysis is a little bit better with Pryor's proportional. Also when I compare it to quadratic. Again, typically I wouldn't even look at this row. I only put this here just to show you to compare with in the past. I would typically always do Pryor's proportional. So linear discriminant analysis gives you a little bit better results. The question though is it enough better to say, yeah, that's a better method? That's debatable. You have to take into the context of the problem here. If If you told a coach, hey, I can use this method and get 87% predictions correct for place kicks, or I could use this method over here and get 86%. That coach would probably look at you strange and think, why does it really matter, 87 versus 86%? But also, though, while it's good to focus on this column, you should also look at the other two columns. How good do we do for predicting successes? How good we do with the failures? And now we can see some differences. And again, let's just focus on the bottom. So, in the real world, if I had to make a choice between these methods, I would really look at that success and that failure accuracy values. And if I was really concerned about making sure I can predict when a failure is going to happen, I choose QDA because it has a higher accuracy value. That's how I would go about doing this. And perhaps, I've thought about this before. What would a football coach want? Would they really be concerned about that failure rate being, that the accuracy for the failures for quadratic being higher? Would that matter to them? I think you can think of it from both perspectives. Yes, it would, or no, it wouldn't. But hopefully in the back of your mind, maybe you're thinking about other situations where, let's say we're using discriminant analysis to predict, does someone live or does someone die? And maybe, you have a clinical trial where you're testing on a new drug. Well, then, one of these accuracy values is probably going to be a lot more important to you at that stage. Are there any questions? So once you make a decision about this, then what you should do is follow up, trying to figure out where is this method failing in terms of the classification so that you better understand it. And so this is then where you can go back to our graphics section and also the principal component analysis section to start looking at stuff through graphs to try to make sense of this. So the code is in the program. So here are the first two principal components, scores. And the first two principal components, the corresponding scores, where the plotting point corresponds to, was it a success or failure prediction? And I made a mistake here where I should have put black. I should put a legend. Black equals failures. Red equals successes. So look at how discriminant analysis is working here. It's saying, let's put the failures for the higher PC number 1 values. Why? Does anyone remember why that might occur? Or does anyone remember what PC number 1 really focused on? Distance, exactly. So if you're a football fan, you know that distance is probably the number 1 factor for a success or a failure. And so we can see how discriminant analysis is really focusing on distance here to make the decision between success or failure. Now, let's actually compare to. Oh, I had that out here earlier, but I must have closed the file. Okay, so this was the original data. Notice how the blacks and the reds were a little bit more mixed up. And so we can see, where are the problems occurring? On the previous plot, we were having blacks all here. But those are ones that we're missing. Okay? And one last thing before I think you have a question.
I was just asked, is this the discriminant analysis or the original failures and successes criteria?
Okay. Notice how I should have brought this up. That black line that I kind of drawn on there, I drew that myself. That's not part of the plot. But notice how it's kind of separating. We're going to come back to that shortly. That's an important thing to understand about discriminant analysis and how it does things. We can also look at then a 3D plot. I already did the code. And you can see somewhat similar results to what we had, what we saw with the 2 principal components. So this is 3 principal components. Look at all the blacks on the left side. PC number 3 doesn't really help us distinguish between the blacks and the reds. And again, these are all the predictions. Okay. So here's a question for you. Suppose I have an independent variable of interest that's categorical or qualitative in nature with, let's say, 3 levels, A, B, and C. I could include that in my discriminant analysis. How do you think that would be included? You know, I mean, think of the matrix algebra calculations that are being done there. You can't put an A, B, and C in a matrix or a vector and do some kind of math with it. How do you think one would account for this in a discriminant analysis? Think back to another class that you've had before. Maybe a regression class. Dummy variables or indicator variables. So for example, what R will do, let's say you had a variable that had levels actually called A, B, and C. What R will do is this. It will create an indicator variable, and for the lack of a better name, let's just call it B. That will be a 1 if it's a B level for an observation, a 0 otherwise. It will create a variable called C that will be a 1 if it's a C variable, 0 otherwise. It will not do A. Why not? For those of you who've had this kind of stuff before.
It would put it as a base, like it would nothing.
Yeah, it will be essentially at the base. So notice, if I have something that's B, I'm going to have a value of 1 and a 0 to represent it. So I have, let's say, 2 new independent variables in my data set that are indicator variables. Indicate, is it a B or is it not? So if you have a B, it's going to be a 1 and a 0. If I have a C in the data set, I'll have a 0 and a 1. And then if it's an A, I will have a 0 and a 0. The key is I have a unique coding to it. That's why I don't need a third indicator variable or dummy variable to represent level A. If you want to know more about doing that kind of stuff, take a look at my regression analysis course notes. I think it's about chapter 9 or chapter 10 that talks about that kind of stuff. Okay, let's see here. Now, sometimes when you teach, over the years you make changes and stuff, and sometimes you have a hard time taking out particular parts of the notes that you like, but you still don't go over them. And I have a section on variable selection here. You're welcome to read it. What this basically says is, okay, let's say you have a large number of variables. Which variables should you include in the discriminant analysis? Should you include them all or not? It's like model selection if you've done model selection for regression analysis. And what people usually do with discriminant analysis, they usually don't address this. And so that's why I a few years ago, I decided not to, but I've written up notes on how to do it, and so you're welcome to see it if you're interested. Okay, let's see. Can I do this? Okay. Now, for the project, you have a case where you don't just have 2 groups. You have, I think it's 7 groups. Well, discriminant analysis works for that too. What do? Well, now you have a mu hat 1, mu hat 2. Let's say we have 7 groups, a mu hat 3 that you're estimating. You do the same thing with the covariance matrices too. You can have a pooled covariance matrix. You can just simply use separate covariance matrices in the same ways that we just saw. So that's why I don't go through it in detail. For Mahalanobis distance, what are you going to do? Well, you're going to be calculating. Let's say if you want to, you have a variable. You have an observation called x. If you have 7 groups, you're going to calculate 7 Mahalanobis distances. The distance that's the smallest corresponds to what you classify that observation into. For the posterior probabilities, you're going to have 7 different posterior probabilities. What do you classify this x into? Well, the corresponding group that has the highest posterior probability. That's it. Now let's say that I have variables x1 and x2. And I did a scatter plot. And I had, let's say, 3 different groups corresponding to x1 and x2. We can see that what discriminant analysis will actually do, it will actually do a good job in figuring out all the correct classifications. It will actually predict everything correctly. And what one can show is actually you could draw straight lines between how the groupings are done. Remember those straight lines that I did on the PCA plot? That's why I did that. Now, will it be exactly straight with principal components? No, because they're principal components. They're not the actual original variable values. Okay? Now, this also gets into, well, where does discriminant analysis fail? It could fail in a situation like this, where straight lines don't work very well to divide everything up. And there are other techniques that we can use if one has to worry about that. I'm going to stop in the notes right there. I know I only had one more thing to do, but I want to go to the project now. So problem number 4 of the project has you use discriminant analysis with the NFL combined data. Part A asks you to use linear discriminant analysis, so the LDA function. Provide a 7x7 classification table. So that summarize dot, what was it? What did I call it? Summarize dot class, that function that we showed, that I showed you. Use that function. Tell me, similar to what we just did, what types of classifications result in the largest correct and incorrect classification rates? Hint, offensive linemen. We do good with those. Part B, try to perform a quadratic discriminant analysis using QDA. There's going to be an error message. You're not going to actually be able to do it. Just tell me what that error message is. For extra credit, you can investigate further about why that error message was actually printed. Lastly, part 8. For 8 points, part D. There's a type of plot, and I had this all open before I got here today, and I don't know what happened. There's a type of plot in the practice problems that I want you to do relative to this particular problem. So in the practice problems, I have a plot that looks like this, where we have 2 variables, simply called variable 1 and variable 2. And I plot the original data with smaller plotting points. The plotting point corresponds to, was it from group 1 or group 2? Then to see how well discriminant analysis does, I plot on top of those exact same points using a slightly larger plotting point. I plot what the classification was, or the prediction was. So for example here, This is an example of a correct classification for population number 2 or group 2. This is a correct for group 1. But let's see here. This right here, it was observed to be population 1, but was predicted to be population number 2. So this is a really, really good kind of plot to do. This is like with the original data, there's only 2 variables. But you can do this with principal components as well, the scores. And then you can see where the discriminant analysis is working, where it's not working, and specifically, like with respect to the NFL Combine data, which positions are being incorrectly classified as another position. So what I want you to do is do this kind of plot with the principal component scores and then interpret it. Let's see if I have that file. Just a second. Sorry to keep you. Okay, well, never mind. So let's take a look what's coming up here. Office hours. Unfortunately, due to the whole budget thing for the university, I have to end office hours at 2:30 because the meeting just came up. Thursday, we got one little thing left to do, discriminant analysis. Then we'll do nearest neighbor analysis. Looking further ahead, project number 2 is due Friday. Test number 3 is Thursday, December 4th. Any questions?
On the project, you said it was number 4. I'm only seeing 3 questions. Is there 4?
I said number. Okay, hold on.
Really? It said put number 4 on. Oh, I think it is.
Yeah. I guess somehow that got in there. I don't know how that got in there. I will say the first draft, I actually had a number 3. Hopefully, in what I gave you, that number 3 wasn't still there. So, okay, that's all for today.